Awesome. Let's get started. So first things first, there is a Q&A tab down at the bottom panel. If you have any questions, you can use that tab, or you can also use the chat. So at some points through the presentation, I can pause and read the questions, and probably if they are not answered by the slides forthcoming, I would answer those questions. So let's get started. So for those of you from outside of Avalara, who am I? My name is Mohan. I'm a software engineer here at Avalara. I organize the Docker meetup in Chennai and also the CNCF meetup in Chennai. These are my handles. So before we get started, what does Avalara do? We are a fintech company. We deal with taxes. Taxes are a 5-dimensional problem. Taxes change depending on what you're selling, where you're selling, when you're selling, and how much you're selling. So my team works to, by this, what I mean is, imagine you have a product. You need to know what you're selling. For instance, the caffeinated drinks in India, they're taxed at a rate different from the normal drinks, meaning Coca-Cola would be taxed differently at a different rate than Fanta, which is taxed at a lower rate. So if you're a seller with 300 million products, how would you know what you're selling unless you go manually read the descriptions? That doesn't scale, right? So we have tooling that will help you do that. So we also have, so these are some numbers. We have 700 integrations with popular ERP systems, and a lot of money goes through us. In 2018, 36 billion in tax remittances went through us. We also process billions of transactions every year. So before we see, like in 2013, if you were following the DevOps ecosystem, you would see everybody advocating for containers, right? Everybody was trashing VMs and everybody wanted to move to containers. But in order to understand why VMs are making a comeback, we need to look what happened in the past. We need to look at the history, right? The VM started in the late 80s when IBM, IBM used to be this computing behemoth, right? So IBM, they were dominating the whole mainframe industry, but the problem was they had separate computing lines for separate purposes. For instance, if you have like an accounting application, you ran that program on a different machine than if you had like a scientific application. So IBM, so imagine you have multiple product lines. Usually what happens is you need to have a dedicated support team for that product line. You need to have dedicated sales team for that product line, and you have all these problems, right? So IBM wanted to like integrate all these product lines together. And so they came up with something called IBM 360. But the problem was there were a lot of these old machines, and IBM 360 was not compatible. The instruction set of IBM 360 was not compatible with these old machines. So what happened was people didn't want to like upgrade to the IBM 360, System 360. And people were in fact sticking to their old machines. So imagine like even these days, right? Machines that are like 3-4 years old are considerably slower than newer machines. So people did not want, like there was a trade-off between hiring programmers and paying for the development cost of porting your program from a 1401 machine to an IBM 360 versus, adding more machines, more 1401s, and people chose to add more 1401s to their problem. They didn't care about the speed. The development costs were prohibitive. So there was a market opportunity, and Honeywell seized it. They released another machine that was compatible with IBM 1401, and they kind of seized that market. But they didn't the translation of IBM bytecode, IBM assembly code to the Honeywell assembly code happened in the software layer. They had like a software translation layer. But the thing was, since 1401 is like an old machine, even though, and Honeywell is a new machine, even though the translation is happening on a software layer, it was much much faster than the old 1401 machine, and everybody started to buy Honeywell machines, and IBM started losing market share. So IBM also, had to get on this bandwagon because otherwise they're going to lose all their customers. This was like the brief history of virtual machines. Everybody did hardware emulation. This what happened, and VMs were did not have much of a show after that for some time. And then in the 90s, you had the emergence of web, and everybody and their neighbor wanted a website, right? America was getting online. You had AOL, and everybody wanted to have their own website. But the hardware costs even today is prohibitive, right? You cannot use one whole server to run just one website, right? Even today. So the hardware cost was prohibitive, and people were trying to do something. People were trying to do something to give access to server to everyone. So you had this emergence of virtual private servers, and you had people who chopped one physical server into a bunch of small servers and gave that out to a lot of small people, like normal people, right? So that's what happened. And then I mean if any of you had been trying to do web development back in 2005 or 2006, right, that's how you would have done it. You would have gone to some host, some server host like Media Temple or HostGator or something like that. How many of you have done? So usually when I do this talk live, I ask how many of you did this. How many of you did this when in 2006? And half the people actually raise their hands, and the rest are like millennials, right? So, and then you had this, and this was on the consumption side, right? And then you had like the lift and shift. So there was this company called VMware. They popularized this whole concept of lift and shift. Imagine without VMs, if you had some application or some DB running on some server, and that server had to be degraded, what would you do? Now you have to like go through this whole painful process of migrating data from that server outside to your new server, right? But imagine your application ran on a virtual machine. All you have to do is just take a snapshot of that virtual machine, and then restore that snapshot on a new virtual machine. That's all. It's going to be seamless, almost seamless. Maybe you can experience a little bit of downtime, but it's almost seamless, right? You had this. So that was the whole deal of virtual machines until very recently. And containers had a parallel and interesting history. Initially, you had just chroot. In fact, that also is like back from the 80s. So there is this command in Linux called chroot. If you just go do chroot in a directory, that directory just becomes your root directory of that shell. And if you execute some command at that point, the command that gets executed will think that the directory that you passed to the chroot is the root command. So that's kind of like a proto container if you think about it, right? This is what we do inside containers, right? The file system inside container is the root for any application or process that's running inside the container. But there is no such thing called a container. There is no such thing called a Linux container, right? Linux container is a colloquial term that we use. What the Linux kernel really gives you is C groups and namespaces. C groups are primitives that you use to restrict the resources given to a process, and namespaces are used to create some level of isolation. Like if you have a process namespace, and if you put a process inside, if you have a PID namespace, and if you put a process inside that, the process cannot see other process IDs. Same thing for network, same thing for file system, and so on. So that's how you achieve this kind of process isolation, and that's what you use to essentially create a Linux container. Even before there was Docker, there was this interesting project called Alexi, right? Because namespaces came from Plan 9, and Plan 9 was in development in the early 2000s, and C groups probably came from Google. And somebody actually combined these two together to actually create a project called Alexi, short for Linux containers. But people were not using this the way we are using Docker today. What they were essentially using is how they were essentially using this was, um, they were using this as though, like, how many of you have used VirtualBox to emulate an Ubuntu system inside your Ubuntu system? They were using it for something like that. They wanted to just have test out operating systems or something like that. They were using things. They were using Alexi for things like that. It was not used for DevOps because it wasn't a term back then. So then Docker happened. So let me just ask you a question, and probably I can read it in the chat. So what do you think Docker brought to the table? So Alexi was already around. Docker did not invent copy on write file systems. Docker did not invent, hosting your images in a different server. Docker did not invent C groups. Docker did not invent namespaces. So what did Docker bring to the table? Any guesses? I'm looking at the chat. Anybody? Okay, so this is what Docker actually brought to the table. So what really Docker brought to the table was a good story, right? So Docker brought to the table the story of a box. About the same time, there was this very interesting book called The Box, right? In 2013, there was this famous book about shipping containers and how they revolutionized the whole shipping industry. Before shipping containers, if you had to ship grains, you needed a grain ship. If you wanted to ship cattle, you needed a special kind of ship. If you needed to, like, there were all kinds of special ships, and the whole offloading and onloading process actually costed a lot more money than many of the goods that were being shipped. So they use that story, and on top of that, there is this, it works on my machine. That is a phrase a lot of people can empathize with, right? A lot of people immediately recognized the problem that they were in. The developer builds it on his development environment, and then he ships it across, and then it doesn't work on the production machine. That's because you have different dependencies and different versions of different dependencies on the production box, and your development box has something completely different. People were trying to solve these problems using things like Vagrant, where you had, like, a reproducible development setup. But this actually echoed better with the developers. People were able to feel better, and also Docker, since it's using containers, it was hell of a lot more responsive. And they also popularized this whole concept of application containers instead of system containers. If you think about what we were doing in Vagrant, we were using Vagrant to create a pristine system in which we can program, right? But Docker was like, let's not do that. Let's just, have only the dependencies that an application need and get rid of everything else, and just ship that image so that you can run it. And not only can you make sure there are no conflicts, you can also reduce the attack surface and remove vulnerabilities. So it made sense. Docker got popular. Docker got really famous, but people started spinning a lot of containers, and now you need something to manage all these containers. So Docker had Swarm, and CoreOS had Fleet, but that didn't actually cut it. So Kubernetes was open sourced by Google. Kubernetes was a re-implementation of Borg. So Google, since they came up with this whole concept of C groups. I mean, the C groups, and they were also using namespaces to isolate their processes inside of Google. They already had everything sorted out. So they basically re-implemented the whole thing again, and in Go, and they just open sourced it. And about the same time, there was this book called book from Google researchers called the Data Center Operating System. And they were basically describing what Google was doing inside their own infrastructure. And they were trying to consider the whole warehouse as a single computer, and the orchestration platform as the operating system. And that also kind of resonated with the developers, and all the developers who thought they would scale to Google scale wanted that. And Kubernetes, when it first came out, used Docker underneath, like the full Docker command, the same thing that you use. That's what Kubernetes initially used. So in order to understand where the new virtual machines fit in, and since I just told you the Kubernetes project was started to manage containers, right? So where are these virtual machines coming from? So let's just take a look under the hood of how Kubernetes actually works. So this is how Kubernetes used to work. Anytime you send a command, anytime you do some modification and there is a difference in state in the Kubernetes master, the kubelet is tasked with creating a container, and then kubelet actually uses Docker, and Docker talks to Dockerd, Dockerd talks to Alexi, and Alexi was used to create containers. Docker initially was using Alexi. But as I said initially, Alexi was about system containers and not, the way we are using it, not application containers. So they actually got rid of Alexi, and they came up with Runc. Runc was a tighter implementation of C groups and namespaces that they were using to create containers. But then something called Rocket happened. CoreOS and Docker, they were buddies, and then they had a fallout. So CoreOS came up with a competing container runtime called Rocket. Now Docker controlled the market, so they wanted something. They wanted to set the standards. So they came up with this whole OCI, Open Containers Initiative, that set the standard for both the container runtime and the images. And Rocket basically adopted the standard. And while doing this, they also had to decouple they also had to decouple containerd from Docker. The daemon that was responsible for listening to your Docker commands, and the daemon that was responsible for creating these containers and making sure that they are still up, were decoupled. They did this for a different reason, which we'll get to on a later slide. But then, what happened? Like I said, that we had Rocket, and since Kubernetes was using Docker and not Rocket, CoreOS went ahead and created something called Rocketnetis, which was just Kubernetes, but instead of Docker, you had Rocket. This is unsustainable, right? This happened in Kubernetes 1.3. What happens when Kubernetes 1.4 comes? You have to constantly make sure that you stay up to date with upstream, so that you also get all the security fixes and the new features. So this is unsustainable. So Kubernetes was like, if you guys wanted to talk to me, you speak my language. And they came up with a new interface called the container CRI, container runtime interface, right? So, but here's the problem: containerd doesn't talk CRI. So they came up with a shim called CRI containerd. And now this is how Kubernetes works these days. If you use Kubernetes, the kubelet talks to CRI containerd, and the CRI containerd goes ahead and does the usual thing of creating the containers the same way Docker does. Let's look at the Docker half of it. So this is how Docker works, but this is true only if you're on a Linux machine. If you're on a PC or a Mac, this is what happens, right? Only the Docker command is installed on the host, and everything else from Dockerd, containerd, and everything else is actually installed inside a virtual machine. They use Xhive in macOS, and they use the actual WSL2. The latest version of Docker uses WSL2 on Windows, which is a virtual machine, essentially. So the bulk of the Docker system actually runs inside a virtual machine, except for your CLI tool. That's why if you don't have Docker running on Mac or Windows, you get this socket kind of error, and the error also says, is Docker running? Right, that's what happens. But if you think about it, if you have the CLI running on your machine, on your side of the machine and you have a VM, the VM might as well be a remote server, right? If you have a remote server where Docker D is running, your CLI can basically talk to that Docker D, and you can actually launch containers on that machine. Imagine you have an EC2 machine and you have Docker D, container D, and everything else running on that EC2 machine. And you use your Docker command line tool to target that EC2 machine. And then if you launch containers, it's just going to happen, right? But here's the thing. If it's a remote machine, all it has to do is just talk the Docker D language. It doesn't really have to be a Docker, an actual Docker system, right? It doesn't really have to use container D. It doesn't really have to do anything. It can just be a web server that responds in the same format that Docker CLI expects. That's what a company called Joint did. So if you pointed your Docker CLI tool to their data center, the whole data center, not a single machine, a whole data center, and if you did Docker PS, it'll just list the containers that you have running. That was like pretty cool at that time. It was like mind blowing. So a lot of people got inspired by that, and they realized, oh, if we can mimic that layer, which has a very standard API, all these layers on the Kubernetes side, they can also be mimicked, right? We can also emulate those layers. So the way Kubernetes master talks to kubelet, that is a definitive API. The way kubelet talks to containerd, that's a definitive API, CRI. And the way containerd launches containers, that's also a definitive API, OCI, right? You have very clearly defined APIs. All these things can be mimicked. So mimic, they did. So if you can see in this slide, I'm going back and forth on the slide. Please look at the page number so that you don't get confused. So if you look at this slide, you have CRI, containerd, and containerd. That's because this is kind of ugly, too many parts. This is because containerd was not created for Kubernetes, right? It was created for Docker. So somebody came up with, Red Hat actually came up with this tighter implementation of CRI. So the CRIO project, CRIO project, is both CRI compliant and OCI compliant. So this is what their OpenShift Kubernetes distribution actually uses. It uses CRIO. And that wasn't the only, so since this is also, the OCI layer is also a clearly defined API, they came up with a bunch of OCI compliant runtimes, container runtimes. The first one was gVisor from Google. So the whole idea of all these other container runtimes is to achieve a different kind of isolation, or in many cases it's like trying to get more security, right? So this whole gVisor project, it was about running your container inside a sandbox. And by sandbox, what do they mean? They have a user space kernel running, and anytime your application wants to make a system call, the user space kernel actually intercepts that system call and decides what to do with it. Maybe it's something it can handle on itself. Maybe it's a system call that doesn't need to happen, or maybe it's a system call that it needs to propagate downstream to the actual kernel. It'll try to use the user space kernel to actually do the operation. And as you can imagine, this is actually quite slow compared to the real thing. And then there is this other project called katacontainers, which takes your container, wraps that on a VM, and then runs it. So katacontainer uses QEMU KVM, which is a very, so KVM is like kernel virtual machine. It comes with Linux kernel. If you enable KVM, Linux kernel basically turns into a hypervisor itself. So you can run other machines beside your machine on Linux while also using your machine. It's kind of like a hybrid type 0, type 1 hypervisor. It's kind of weird. So katacontainers actually used QEMU KVM to create these virtual machines and container. Put your container inside that. And katacontainer also handles, so one of the responsibilities of this container runtime is to make sure that your container is actually running, right? What if some seg fault happens and your container crashes, or it exits with a non-zero exit code or something like that? It needs to make sure it is still alive. right? That is a responsibility that the container runtime has. And kata container, since it's running inside a virtual machine, you cannot see from outside what's happening. So kata container bridges the virtual machine and the real host machine, make sure that all these liveness and everything is propagated to the outside world. So that's what kata container project does. Um, but the but the problem with this kata container project is it is using QEM UKVM, which is the same thing that people use. It is similar to VirtualBox. It has all these fake devices and it has everything. It has all these fake mouses, fake keyboards, all these things that when you try to launch a VirtualBox kind of setup, a machine inside a machine kind of setup on your laptop, it has something similar to that. So a lot of all those things that you don't need when you're trying to just run an application. Your application probably doesn't need a fake keyboard, right? That's the problem with this project. So why are these people trying to run virtual machines inside Kubernetes, right? Isn't the whole point about containers? And everybody wanted to, move away from. If you remember back in 2015, 2014, everybody was trashing virtual machines. They were like, virtual machines are archaic. Everybody needs to move to containers, right? So why is everybody suddenly using virtual machines inside of Kubernetes, the project that was built to actually run containers? So you have a lot of cases. Most of it is about security, right? You have shared devices. If I have multiple containers from multiple different people running on the same host, if any of those containers have some vulnerability, that's going to leak, right? Because I have a shared, let's say I have a shared peripheral device and that driver actually has some vulnerability, then that's going to, any code that's executing inside a container can exploit that vulnerability to also compromise the other containers. And you also have growing system calls, the seccomp profile. So containers also, in addition to C groups and namespaces, the containers also have a seccomp profile, which is used to either blacklist or whitelist a system call. But that's kind of tedious, right? What if you think that an application doesn't use a system call and you have blacklist, you have a whitelist of system calls, and suddenly the developers use a different function, and that function is actually doing that system call. It makes ops very difficult. So if you use a blacklist, the the next version of kernel will have a few dozen more system calls, and some of them could be ones that you want to restrict, and that's going to basically make the whole seccomp profile meaningless. Then also you have the problem of noisy neighbors, right? What if I have an application that's writing a lot to disk and it's also reading a lot from disk, and you have some other container on the same machine right beside it? The other container, maybe it's like a web server, and that's going to have performance degradation because of this, right? And what if I have some container that's basically just trashing the network port? I'll have basically no way of my container, the good container will have no way of actually accessing the internet then, right? So you have this problem of noisy neighbors, and there are existing workloads that only run on virtual machines, right? You cannot just readily containerize a lot of legacy apps that were built, let's say, even in 2000s. You cannot just readily containerize them. They are huge monoliths, maybe they are stateful. So you still want to like have them in a virtual machine setup, but also you want to like leverage the whole Kubernetes ecosystem. And there is this category of workloads that are a pain to run inside a container, right? So at work, we used to have a Chromium cluster to render pages and extract pages. Like you have a lot of PWAs, right? You cannot extract information from them unless the page is actually loaded. And we actually render pages at scale. So Chromium, until the Puppeteer project came out, and even after the Puppeteer project came out, it is a real pain to run. It was a real pain to run Chromium inside a Docker container. So we had to basically run them as AMIs on a separate cluster. We were not able to containerize them. So these are the cases for virtual machines. So it was a compromise, right? If you wanted density and speed, you had to choose containers. If you wanted security, or if you had existing workloads that only run on virtual machines, you had to choose VMs. All in perfect balance. Your choices are clear. You choose either that or this. It was then it all changed when AWS announced Firecracker. So Firecracker came out. They promised 150 millisecond boot speeds and density on par. Nearly, you can have thousands of containers, thousands of virtual machines, Firecracker virtual machines on a single host. So these are the same promises that container gives, Linux containers gives you, right? Docker gives you. So you had the same level of density and you had the same level of boot time, boot latency. So in fact, before that, you had this paper came out at the height of the Docker container hype cycle. You had this paper come out. It was titled "My container is lighter and safer than your my VM is lighter and safer than your container." So in this paper, they describe how they achieved 150 millisecond latency. Basically, if you remember when I was describing QEMU, KVM, you had a lot of these fake devices. You had this whole um, drivers for these fake devices and all those things that you needed to initialize before you could run your actual application. They got rid of all that, and they also got rid of any limits on, like, generally when you start a virtual machine using VirtualBox, you pre-allocated like 2 gigabytes of RAM or 4 gigabytes of RAM to it, right? So that's why you can have only so many virtual machines on your machine. Imagine you have 16. If you have a laptop with 16 megabytes of RAM, the maximum you can run is like 4 virtual machines of 4 gigabytes each. So this paper got rid of that notion. It was like we can allocate memory just like we allocate memory to processes, and it achieved a very lightweight container, which if you can Google this paper, you can read the rest of the paper where they'll show graphs where the performance was on par with the Docker containers of their day. This paper is actually from 2017. So Firecracker, when it came out, Firecracker itself is actually a fork of cross VM from Chromium team. But Firecracker is written in Rust. So Firecracker promised thousands of containers per host, 150 millisecond startup time, and real isolation, unlike Docker containers. And the way it achieves that was, like I described, it still runs on KVM. So KVM gives you the ability to leverage hardware level virtualization. So if you're on Intel, there is something called VT-X, or these special instructions that you can use if you are virtualizing, if you are a VM. So KVM already gives you the ability to leverage those instructions. So your process runs as though it's on the host, even though you have isolation. There is no performance difference between a process running on a host and running on a guest if you're on KVM and if you're leveraging all the hardware capabilities of hardware virtualization capabilities. So like I said, they stripped down the device profile. Firecracker gave you only 5 devices: a block device, a device for like a 1-button keyboard to give you an interrupt, network device, and then a couple of more devices. They had the device profile set to a minimum, and it's also written in Rust, which they say protects us from a class of problems where you kind of try to hit a memory that has already been claimed. So a whole class of vulnerabilities are actually created by something called use after free, where your code is actually trying to hit a block of memory that it doesn't have access to. So you can actually get, since it's written in Rust and Rust won't compile if you're trying to do that use after free, you can get rid of that whole class of problems. And the best thing about Firecracker is the whole thing is actually managed through a HTTP API. They actually have a Swagger endpoint. If you go to Firecracker API, you can just do get and post calls to get the information about processes running inside your Firecracker VM. If it's like a container, I mean, containers are also processes, right? You can essentially post something to make something happen inside the virtual machine, and you can get something to get the status of processes running inside the virtual machine. So how does Firecracker fit into the old diagram that we saw? So if you remember the Kata container project, it was using QEMU KVM. So you can just replace QEMU KVM with Firecracker, and that's another virtual machine manager that you can use to achieve achieve isolation for your containers. So this is one project that uses Firecracker. There is also another project called Firecracker Containerd. So if you remember in this slide, you had Containerd here instead of Cryo, right? So you Containerd's objective is to make sure that the containers that it spawn actually is in fact running, and it also has to group all the statistics and send it back upstream to the kubelet. So if you have a project called Firecracker Containerd, and that project essentially gets rid of this whole part below this, and instead of creating containers, it just launches a Firecracker virtual machine and then just runs your container inside that. And then you also have these projects called Ignite and Firekube from Vworks. So they're using, like, the first two projects, they're using katacontainers, I mean Firecracker, as a way of achieving isolation. But Ignite was like, let's not even create containers. Let's just create a virtual machine and then download the whole container image and then layer it on top of that virtual machine. So that's a very interesting project. So you have the Ignite project. It has the same interface as the Docker command. So just like how you do Docker run or Docker start or Docker stop, you can do run, stop, start, just like it has the same interface. So if you just do Ignite pull, it'll try to pull an image from the Docker hub. It'll try to, let's say if you do a Postgres image, it'll try to pull the Postgres image from the Docker hub. It'll spin a new Firecracker virtual machine with a guest kernel as well. And then it'll unwrap this container image that it just downloaded from Docker hub. And then it'll layer that. So container image is basically a group of file systems, right? It's a set of file systems, one layered on top of the other. So it'll unwrap the whole file system, set of file systems, and put that on top of the virtual machine it just created. And Firekube is something similar to, I'm not sure how many of you are using Docker on Mac. So if you're on Mac, you already have, if you install Docker, you already have Kubernetes, right? All your Kubernetes components are actually running beside your Docker, on the Docker virtual machine as containers. So there is another project called KIND, Kubernetes and Docker. All the Kubernetes components run inside Docker as though they are containers, and they have the ability to spawn new containers. It's kind of like a inception level thing. So Firekube does the same thing so since Docker has the ability to do that, if you have the, let's say, think about it this way. If kind is what, so Firekube is what kind is to Docker. All right. So I might have confused. So you can basically use Firekube to spin a Kubernetes cluster. Let's just put it that way. So these two blog posts actually came out back in 2018. So there is a principal engineer in the background. You can see a principal engineer from Pivotal who says the future of Kubernetes is virtual machines, which means you use Kubernetes to control your virtual machines. And in the foreground, principal engineer from Red Hat says Kubernetes will start to replace hypervisors. So they're both saying they're both telling us the same thing, except in the reverse way. So you see projects like kubelet which I was discussing about existing workloads being a pain to migrate to Kubernetes ecosystem, right? There is a project called kubelet, which can, make your take your existing workload, put it inside a package, make it container compatible so that you can orchestrate that using Kubernetes. So that's what happened. So the whole point of this is, let's say you have a huge company and you're constantly innovating. You have multiple deployments happening every day, and people are constantly like, think about this for a second. How did Git change the way we work, right? Before Git, you had to like make sure that you don't change something bad, and you don't change something that's important and make the code bad, make the code not unbuildable. But Git changed all that. Now you just push to a PR, and if there are merge conflicts, you just resolve that when you merge, right? The same thing happened with systems like CI/CD, where if there is something that's broken by your change, the CI system just reports it just after the merge, and then you can just go find that and fix that as soon as possible, right? So this kind of gave you a confidence. You cannot possibly break things. In fact, when in my first job, when the week that I joined, my mentor told me, no matter what you do, you cannot possibly destroy anything, because the infrastructure that we had, like the whole data and everything that we had, was reproducible, and I cannot possibly damage anything that we had in an unrecoverable way. Let's say it might take some time to recover, but there is nothing. I cannot cause irreparable damage. That gave me a kind of confidence. In fact, the one time that I had to do something that I know would cause an irreparable damage, I did the dev work in like 2 weeks, and then I took the next 3-4 weeks trying to run several trial runs to make sure I don't destroy like the whole data set. And the data set actually takes like a whole year to recrawl, right? So I don't destroy the whole data set, or I don't pollute the data set with bad data or something like that. I had to spend the next 4 weeks trying to make sure that what I am doing is in fact right, and it won't cause bad damage. So imagine you give your developers a platform in which they can just deploy their application and not worry about all these security vulnerabilities and seccom profiles, and calling your ops people to essentially release abilities and all these things. So if they have that confidence, your release cycles are going to become smaller. I mean, you can push features sooner than you would, and since they are confident, they will also work faster. And think about the amount of time saved. Think about the amount of money saved. So that's the whole talk. So this is my GitHub. This is my LinkedIn. If I see there are a few questions, let me just answer them. Yeah, okay. Manish is asking noisy neighbors. Noisy neighbor applies to VM as well. Okay, so there is a noisy neighbor problem, like I was discussing in containers, because you have multiple containers running on the same host, right? But in Firecracker, you have something called Virtio FS and Virtio.net, Virtio-net. These are virtual devices. And these virtual devices, the way they work is they have to copy from one buffer to another. And when they do that, they actually use a token bucket algorithm, which means, unless you have tokens, you can basically do rate limiting and throttling at that point, which means if you have multiple Firecracker virtual machines, if one is trying to hit the disk or network way too many times, you can actually throttle at the Virtio level. Manish, does that answer your question? All right. Does anybody else have any questions? Okay, major differences between AWS and Docker. So Docker is essentially a tool. It's not a IaaS like AWS. AWS gives you EC2 and all these virtual servers, right? Docker is just a tool that you use to create containers. They're not actually related at all. In fact, you can spin up an EC2 instance. You can have Docker-D, like I said, running inside your EC2 instance, expose that IP, point your Docker command to that EC2 instance, and then you can deploy containers inside that instance. Anybody, guys? Any other questions? So there is a Q&A tab which you can use to answer the questions if anybody joined late. All right, no more questions. See you guys next time, I guess.
Right. Thank you, Mohan, for the interesting session. And everyone, if you have any feedback, any comments on the content of the session, or if you have any suggestions for us for our next topic, leave us a comment on our meetup group. That's Pune Tech Talks. Thank you so much for attending.